In this example, we're looking at the Bohr-Rutherford model and showing that the Bohr radius is about a half an angstrom and the ground state has an energy of minus 13.6 electron volts. Now, all of these formulas in the Bohr-Rutherford model have a lot of constants in them with a lot of powers of 10, and so I thought the most efficient way to work in these types of problems is to have a spreadsheet where all the constants are written out, and so we can just click on them and put them into formulas. So I'll post this spreadsheet on Moodle so that you can use it as well if you want to. So we have the constants of nature that we'll be using: Planck's constant, Coulomb's law constant, the elementary charge, electron mass, and speed of light. And then over here I've started some formulas to show you that the Bohr radius works out to be 0.53 and that the ground state energy works out to be minus 13.6. But I'll show you the details of those by clicking on the cells. So for the Bohr radius, let's go too far. Here we go. For the Bohr radius, we're using this formula for the radius of a hydrogen atom and plugging in the value n equals 1. So the Bohr radius corresponds to the radius of the hydrogen atom when the electron is in the lowest energy level, known as the ground state. So n equals 1. And so to calculate it, we need to take Planck's constant and square it, divide by 4 pi squared k e squared me. And so that's what I've done here in the formula. So C3 is Planck's constant. Let me click on it. Okay. C3 is Planck's constant. 4 times pi squared. I'm not sure how well known this trick is, but to put pi into Excel, you actually need to write pi and then open parentheses, close parentheses for it to recognize pi. You can't just type pi like you can in Google. And then C4 is the Coulomb's law constant, and then C5 is the elementary charge, which gets squared, and then times C6, which is the electron mass. So we're doing this calculation here for the Bohr radius, and it equals 5.293 times 10 to the minus 11. We want to convert that to angstroms. An angstrom is 10 to the minus 10 meters. So to go from meters to angstroms, we need to multiply by 10 to the 10. So I take the number here, multiply by 10 to the 10, and then I rounded it, so you get 0.53 angstroms. So that's where this number 0.53 comes from. Now for the ground state energy. This is the formula for the energy of an electron in the n energy level. Okay, so this combines the ideas of kinetic energy, Coulomb's law for the potential energy of the electron, and then also you're factoring in the fact that the angular momentum is quantized, and that's where this n and h come into play. You put it all together and do a lot of simplification, and you can get the formula into this form, where we've eliminated velocity and radius. So everything in here is a constant except for n, and in the spreadsheet I've calculated with n equal 1, 2 times pi squared, C4 is k squared, C5 elementary charge to the 4th, C6 is mass, and then C3 is Planck's constant squared. So we've done all of this calculation here with n equals 1. To get a ground state energy minus 2.179 times 10 to the minus 18. But since I've kept everything in standard units, all of these constants are given in standard units, that means the energy I'm getting is in joules. So to compare it to the formula here where it's given in electron volts, I need to divide by C5, the elementary charge. So to go from joules to electron volts, you divide by the elementary charge, and that's where the 13.6 comes from. Okay, now a little bit more. We can make a general formula for calculating the radius in angstroms, the energy in electron volts, for any energy level we want. And the way we do that is we take the, well, let's go back to the radius formula. We take the Bohr radius and multiply by n squared. So equals the Bohr radius times n squared. So if I put the energy level here and square it. And then for the energy, I take the ground state energy and divide by n squared. So over on the spreadsheet, equals the ground state energy divide by n squared. And now I realize I did this correctly for energy, but I didn't for radius. For radius, I want this in angstroms, so I grabbed the wrong radius. I grabbed it in meters. If I want it in angstroms, I need to use F3, not E3. Okay. Now I'm going to format this so it's the same. Let's see. Okay, so when I have the first energy level, then this is just the Bohr radius and this is the ground state energy. If I want to pick some random level, let's go up to energy level 4. Now I can calculate that the radius is about 8.5 angstroms, and the energy of the fourth energy level is minus 0.85 electron volts. And this would work, this calculator here would work for any number you want to put in. If you want to put in the 12th energy level, you see it goes to minus 0.09 electron volts. Now this is useful for a couple of reasons. If you have a calculation that you just need the number, you can plug in here, but you can also start to see what's happening as you increase the energy level. As you increase the energy level, the energy is going up, but they're going up from a negative number and getting closer and closer to 0. So if I put the energy level 108 in here, this number is getting very, very close to 0. And that's what happens with the energy levels. They get closer and closer spaced together and closer to an energy of 0. Energy of 0 corresponds to the electron coming free from the atom. The energies are negative, meaning that they're bound to the atom. So in other words, they have more potential energy than kinetic energy, right? If their kinetic energy overcomes the potential, then they can break free from the atom. And the critical point is when that energy is equal to 0. So at the top energy level, you get an energy of 0 and the electron becomes free. Now, what happens to the radius, or what happens to the size of the atom? You can look at that as well. So let's go back down to, let's say, n equals 3. So the atom, the size of the atom, when the electron is in n equals 3, is about 5 angstroms. So it's about 5 angstroms from the proton to the electron. If the electron jumps up to a really, really, really high energy level, like let's go back to 108, now it's getting to 6,000, over 6,000 angstroms in size. Okay, so you can see what happens to the radius. Because the radius gets multiplied by n squared, the energy gets divided by n squared.